Okay, so today we're going to be walking through what is graph learning, and this is actually the recorded section, or the video that we're going to be uploading that goes with this article. So we're going to be, I guess, exploring specifically the multi-layer perceptron algorithm, and we're going to be exploring the graph variant of it. Kind of, I guess, the generic variant that's used today mostly. And the reason that we chose this, the multi-layer perceptron, is because it's kind of like at the core of all of deep learning, or most of deep learning. And as we know, I guess today, 2021, deep learning is kind of like the de facto or the most common approach to learning algorithms. And I think it has to do a lot with it's kind of like deep learning takes a more sort of declarative approach to learning the representations of the data. And this is thanks to something called the universal approximation theorem, which says that every time we iterate through the data, we're actually learning features, or we're adjusting the weights or the parameters that we're learning. And this is actually thanks to the nonlinearity function that we'll be talking about further down. But basically what this says is that as a result of multiple iterations to the data, at the end we're going to be left, or we're going to automatically generate a function that kind of describes the data, or the important features, if you will. So yeah, we've chosen to represent data as graphs, and this is just because graphs are extremely good and efficient at representing relationships among entities. And maybe a few examples of this can be like telecommunication traffic, so think cell phone towers and whatnot. Computer grid networks, chemical compounds. This is actually pretty cool. This is being employed in for drug discovery, and social networks, and many others. So I've seen, for example, DeepMind is using graph methods in order to kind of solve the protein folding problem, and there's another really cool project. It's called the Wolfram Physics Project, and there they explore the fundamental properties of physics, and they also employ graph learning, and they actually have some very pretty visualizations of what they've discovered. So usually during the initial stages of learning, or the first iterations, of course we need to have we need to start with a set of observations, right? And based on these set of observations, we can then start to kind of derive the initial structure of the data, and then from there we can start doing some other kind of interesting stuff. But at the beginning, we need to learn structure. So okay, so here I'm going to talk now that we talked about the graph representation of data, and we'll go further into detail down the article. I just wanted to talk a little bit about the machine learning algorithm that we're going to use, and it's the MLP, Multi Layer Perceptron algorithm, which, as we mentioned, is at the core of most of deep learning methods today. And maybe just a brief history. So the first time that this kind of perceptron idea was defined as quantitatively was back in 1943. So it was by McCulloch and Walter Pittis. And the paper they had, you could actually look it up online. It's called Logical Calculus for Nervous Activity. But what this says is basically, okay, we have a perceptron that's taking, and this is actually based on psychology initially, and how our perception works. And they did like biological experiments on rats, I think, and they actually found that this was true, that perception actually changes the brain sort of structure. It morphs it in a sense. And I think they did it by by taking two, I guess the experiment was they had a set of rats that were exposed to daylight, and then they had a second set of rats which actually lived in the dark, and then they found out that that their neural activity was completely different or somewhat different. So basically it says, okay, we're going to take, let's say for instance the eyes. We're taking sensory information through the eyes. And our neurons are receiving different inputs. They're aggregating. This neuron is aggregating and then passing on whatever data or useful information it's gathered from the sensory data, and it's passing it to the next set of neurons. So then in 1949, Donald Hebb, he contributed that he said, okay, of course there are many of these neurons in our throughout our body, right? So what Donald Hebb says, okay, usually these tend to create a structure. Like the nervous system, the neural system actually starts creating a structure, and usually this arises when neurons start to fire close to each other. So now we're saying, okay, structure is starting to arise. So this kind of has its this kind of models the models that we create and save. So that's kind of like the original thought. So then I guess the first experiment actually on a computer was done by Frank Rosenblatt at Cornell University. And this is actually the paper that they published. I know it says 1959, but yeah, they're different. This is actually the paper, but the actual experiment was in 1961, and this was done on an IBM. Was, I guess, like even the previous to transistors. I don't know what. I think it was like vacuum tube-based computing computers where they did this, in IBM 704. So that's just a kind of history of when the first perceptron was actually programmed into a computer. So now, fast forward to today, we're going to be exploring the Mlp algorithm, and maybe we're going to be talking about what it looked like and kind of like the common approach. So there's like, how many steps do we have? Six or seven steps. And so yeah, let's just go ahead and walk through it. So I guess this is the Mlp algorithm, okay? So the first step is that we have to sample a mini-batch. Why do we do this? Usually, so we have a set of inputs. Let's say that we have x1 and x2. These are our input parameters, and usually these can be in the order of, it depends on the use case, but it can be millions of parameters. So it's very inefficient to kind of compute over the whole data set. So that's why we operate over many batches of data. So we kind of said, okay, what the size of our mini batches, and that's what we're going to be using throughout, like our forward pass and our back prop and so on. So after note that we're going to select a different batch at each step. So then the second thing we do, once we have our mini batch of input features, let's say we selected x1 and I don't know, a few here, we're going to select the mini batch, and then we're going to matrix multiply. Let's say that during the first pass we can even set these to 0 or a random number. It doesn't really matter. We can set the random number. So we multiply the first. So for simplicity, let's just say that this is the mini batch. X1 and X2 is the selected mini batch. So these are going to be the input features. We're going to matrix multiply with whatever. Let's say the first this is the first pass. We're going to matrix multiply by the weights 1. Now this is called actually a hidden layer. Then we're going to go ahead and matrix multiply by the second hidden layer, and then we're going to obtain a function at the end. So this would actually The last layer usually represents the categories in which we're gonna classify. So let's say that we wanted to do a binary classification to see if a molecule, and we'll talk about, so we're gonna actually do our example with a molecule, right? But let's say that for our molecule, we wanted to determine if it was if it's mutagenetic or non-mutagenetic. So we would have two output features at the last level of the neural network, right? If we had, let's say, that we wanted to classify from 1 to 10, we would have 10 in the output. Let's say that we wanted to classify between dog, zebra, and cat, then we would have 3 in this output, okay? So once we've actually done our forward pass, and we've obtained kind of like the features, and we've just basically done matrix multiplies, we kind of frame this as a loss function. So we try to determine, okay, given these features, we've done the forward pass, and then here our algorithm guessed that it was going to be a cat, and actually we were wrong. So it was not a cat, it was a dog. So that's our loss. We need to compute some loss at this end, and we say that we do actually know what was the real value, because we start from an initial set of observations in which we know we know that the true label for what we're trying to predict. So once we actually calculate the loss, a common approach is to use cross-entropy loss. Then that's the first portion. So as we said, we're going to compute some loss here at the end, and it's just basically a discrepancy between the true value and the predicted value. So this is, I guess, the algorithm, but we use cross-entropy, and then we get a total loss. This is just saying, okay, we're getting a total loss. And then something to note here is we actually, at every layer, we're going to apply nonlinearity. This is a little bit of what we alluded to earlier. This nonlinearity, usually it's the ReLU function. It's the rectified linear unit. What it does is actually, it helps the process of convergence. So this is what actually guides the iteration to kind of converge to the universal approximation theorem that we talked about earlier. So what nonlinearity is going to do, specifically this ReLU, is after all these after each matrix multiplies, so let's say that we multiply X matrix by W matrix, in between here, right after here, we would apply a ReLU, which basically says, okay, whatever negative values you obtain, set them to 0. So yeah, that's basically ReLU, setting negatives to negative parameters to 0. So then we would, during our forward pass, we would multiply the weight 1 with weight 2, and here we would apply again another ReLU. So we would apply a ReLU after each multiplication by a hidden layer. Okay, that's all ReLU is, and that helps the iteration converge toward kind of trying to find out the function that we want to try, the function approximation. So after we've done, or we've completed kind of like the forward pass, now we want to kind of go backwards. So we're gonna actually calculate the derivatives of with respect to the loss. So remember that we mentioned that we computed a loss score, and we kind of want to go backwards. We want to propagate this loss backwards, and then update these parameters and get them ready in such a way that it's going to minimize the loss in a future iteration, right? In a next forward pass. So again, we calculated a loss, and then we're going to backprop, which we'll share a little bit how to do it in a little while. So we're going to kind of we're going to backpropagate the loss, and then at each hidden layer, we're going to update the weights in order to, for next iteration, to lower, to have I guess, a better a function approximation of the real value. So that's basically backpropping, okay? Oh, and here it's actually described. So we're going to start with the loss, and the way we do it is, okay, we take the derivative of f of x with respect to the loss, and then we start going backwards. So then we start w2 with respect to f of x, then w1 with respect to w2. So it's just a derivative. So that's actually backpropagating. But there's another step. While we are actually backpropagating, we need to know, okay, so yeah, I know that we were far away from the loss, but okay, for these parameters, am I going to update them in a positive way or in a negative way, or how am I going to update these parameters in order to decrease the loss during our next iteration? Okay, so that's where gradient descent comes in, right? So what gradient descent helps us do is try to determine, okay, how we're going to update these parameters such that whenever in the future past, whenever we matrix multiply, this loss will go lower to 0. Okay? So this is just, I guess, the verbiage. So here we're saying, okay, we want to actually optimize we want to minimize the overall loss score. We're going to use stochastic gradient descent for this. And we'll talk about that. So this is actually a picture of stochastic gradient descent, and I'll tell you what this means in a second. So after we've obtained the gradients of each hidden layer that we computed in step 5, so remember that we calculated each derivative in a backward way, then we need to determine, okay, in which direction am I going to update the parameters? Am I going to add more positive values or more negative values such that it's going to optimize the loss, right? So remember, we've backpropagated the loss. So now whenever we run stochastic gradient descent, each hidden layer is aware of what loss, what was the total loss, and so yeah. So here we're going to introduce 2 additional hyperparameters that help select kind of like the direction in which we're going to update our hidden weights, parameter weights. And another sort of, after the gradient determines the direction in which we're going to update, so let's just say positive or negative, we also need to know, okay, by how much do we want to update our weights? So what if we update our weight here, like say +7 or +100? So as you can see, as a general rule of thumb, we're going to start with kind of larger sort of updates, and then we're going to slowly start to decrease the size of the updates or the steps that we take as we find the local optima. So that's actually what the learning rate is. It's kind of like the step size that we take. So here we would go at, I don't know, the first iteration might look something like +100. Then the second iteration said, oh, we overshot by a lot. Let's actually do +20. And then the third one is +3, and so on. So as we converge toward the optima during each iteration. And the atom optimizer, this is actually just I guess this is the de facto or the industry standard for computing individual learning rates adaptively. So what this says, it's just that each hidden layer, it's going to have its own kind of depend on itself. Each parameter. So this is going to do it for each layer for each parameter, right? And it's going to do it adaptively. So it's going to start with a large, probably a large step size, and then start minimizing or making smaller step sizes each time. And mini batch. Okay, so the part mini batch here and the mini batch stochastic gradient descent is actually the same concept as before. So we're doing this over many batches and not the entire data set. And this is for computational efficiency. So ideally, we would want to stop training once we're kind of like within this ballpark, or whenever our learning rate is no longer increasing. That's when we need to halt the program and say, okay, this is kind of like the model. Save the weights, and we're done. And then whenever you want to kind of predict, all you need to do is for prediction is we're going to be loading whatever we saved as weights, as the last weights. We're going to save them. And then whenever we actually need to, during the exploitation phase, we're going to load those weights and do one forward pass on the data. So we're going to load, these weights are already going to be kind of like optimized, pre-computed. We're going to give it new data, and we're going to pass it in through the saved weight networks, and then it's going to print sort of like a class, or whatever it's the highest probability of event being in a class, and that's going to be kind of like how we do prediction. Or generation, depends on the problem. So for this purpose, we're going to do prediction. But usually, I guess whenever, as a side note, whenever we hear generation, it's actually just the same as prediction, but with a twist. Okay, so that's pretty much the theory behind the multi-layer perceptron, which is at the core of deep learning, right? So there are various extensions, such as, I guess, the RNNs, LSTMs. That's for kind of like time series analysis. And then there is also the convolutional neural nets, or convnets. And actually, we're going to do, well, but that's usually used for images. Okay. So for today, we're going to be going over the Mutec Data Set, which is a collection of chemical compounds. It's very small. It includes 188 samples. So it comes with its problems, but for this, for today's demo, it's good enough. So these 188 chemical compounds, we're gonna represent each of them as a graph, and I'll show you an example right now. Each graph is labeled with there are seven discrete node labels, which is actually the atom annotation. And then there's two classes at the end, which says, okay, is this mutagenic or non-mutagenic? Which means, does it cause or does it not cause a change in the DNA to whichever it's applied? So remember, if we go back here, it's going to have two output layers at the end, or two output parameters. So as we said, this is chemical compounds. Okay, this is important. So we're going to represent a graph right here. So this is actually a real graph of one of the chemical compounds. Here as a note, here hydrogen atoms have been removed, and vertices or nodes are labeled by atom type. So here are the seven, 1, 2, 3, 4, 5, 6. I probably missed. Okay, here are the seven classes of data, right? So those are the seven atoms it can take. Okay, and now we're going to kind of go through what a machine learning pipeline would look like. So how would we actually take the data? How would we pre-process it, which is actually, I think whenever we talk about graph data, really what we're talking about is this pre-processing phase, or how we represent the data. Because training and prediction is actually the same for, it doesn't really have to be graph data for this portion. So it's just more in how we represent these relationships. Okay. So yeah, as we said, a typical ML pipeline looks like this. So actually, there's a link right here. It's a GitHub link, and so we're gonna first set our prerequisites. Okay, so we're gonna kind of expand on these topics further down. So for today's walkthrough, we're going to be using Rust language, and And we're going to be using a library that has C++ torch bindings because remember that these deep learning methods rely very heavily on matrix multiplication. So we're going to need a library or something that helps us efficiently matrix multiply. And torch seems to be pretty cool because you can use CPU or GPU, whatever hardware you're on. And so the library that we're going to use for this is TCH library. It's a very cool library. I would encourage you to explore it. For the pre-processing, we're going to be using petgraph, but we're not going to be using this for the training and predicting phase. As we mentioned, graph is kind of more just for like representing the data. Okay, so about the data. So here, actually, in this, here's a GitHub link, which I'll go ahead and show right now. We're also going to need the data set. So I've went ahead and pre-processed the data. So we're not going to go too deep into how we pre-process the data, but maybe I can talk about it and give some intuition. So here's the link. Maybe. Yeah. Okay, and well, that's at it. So here, as we mentioned, okay, the original data is right here, just in case if you want to explore it. These are the pre-processed sort of train. So we've taken the data, we've already pre-processed it, and we've split it, right? So this is where, because really what we want to show here is well, we're going to show the MLP algorithm. So we've already taken this. So X concat means, okay, these are the tensors that represent the training data. These are the labels for the training data. So the labels mean mutagenic or non-mutagenic. And this is for this test set. So I think it was something like 170 samples here and 18 sample for the tests. And we've also added in a unlabeled sort of chemical compound, and this is kind of to see if it can to show how prediction works. So pre-processing. Okay, there are many ways to pre-process graphical data, but for this case, we're going to represent each chemical compound as a graph, right? So we're representing each compound as one of these, where each graph is represented as a 2D matrix. And I'll give some visual into it. So yeah, this is a little more visual intuition. So each graph is a 2D matrix, and what does this 2D matrix mean? Each row represents a one-hot vector encoding of a node. So each of these is a node. In this case, it's an atom, and it's going to have it's going to be one hot vector encoded. So this is actually not the example in the Mutec data set, but I just wanted to show it to give some visual understanding. So we're going to have actually one hot vector encoded, and we and each tag represents the type of atom. Okay, we've talked about this. Okay, we've talked about the binary label, if it's mutagenic or not. So this is a little bit about the data, how we pre-process the data actually. So we're gonna, at the end, we're gonna be processing or machine learning with this. We're gonna be computing with this 2D matrix. Okay. So this is actually kind of cool that we could represent atoms as computational graphs. So for splitting, we used K-fold algorithm. And what this does, it's just kind of it just gives the indices to choose from for your data set. And after you've split the data, you've pre-processed it and everything. So we're ready for the training. We're ready to do the actual forward pass and the back pass and learning and saving the model and all of that good stuff. So here's actually the code. The prerequisites, if you don't have Rust installed, here's the process of how to install Rust, how to test, maybe test that you have the version. We need to download the torch bindings for C++. This is how to do it. The directory structure of this project, what we'll be running today, and the results. So before we, so I've pretty much done all this already, and we're gonna just kind of walk through these two commands, which is actually going to be right here. So first, we're gonna train our model, right? So as I mentioned, we're going to be loading our data from the directory, which is preprocessed data. Oops. So let's see if I can show the directory with the data. So we're going to be loading the training files and the test files. After this, we're going to actually, well, set them to a tensor representation. So let me just show the training files where they should be. So data set, and this is where it's all at. So what this is going to do is, okay, our variable store, we're just going to set it to use a CPU or GPU. So this is going to be whatever is you have on your machine. It can run on anything. Here we're actually defining the model. So we're going to set the number of layers that it's going to have, our input dimension, and our number of classes, which is the output dimension and the hidden dimension. So I'll try to show it up here. This is actually where we create the multi-layer perceptron, and we'll just be using a sequential here, which a sequential is just kind of like a handy way to create a neural net. So you can just kind of put each layer, kind of define each layer. It's kind of like a neural net on the fly, right? So as we mentioned, we're going to actually do a matrix multiply. We're going to matrix multiply the input by the hidden dimension, and then we're going to do ReLU, as we talked about earlier. And then we're going to do this by the second sort of set of weights, and then we're going to ReLU again, okay? And then that's kind of going to represent the forward pass. So that's going to be our MLP model. We want to set our, remember we talked about the gradient descent, so stochastic gradient descent. So one thing to note here is that we probably don't need to use mini batch since this data set is very small. So we're just going to be using kind of like the atom optimizer. So this is going to, we're telling it we want the atom optimizer to kind of let the iterative process know how to update our how to update the hidden dimensions, right? As we talked about a little bit earlier. So it's going to do this adaptively, as the name says, adaptive, I think momentum or something like that. And it's going to determine the learning rate, so the step size, how we update our weights. And here we just say, okay, well, let's go ahead and train. So we're going to start. So here, I guess for each epoch, we're going to calculate a loss. We're going to do a forward pass. We're going to, remember we said that the way we calculate the loss is by Cross-Entropy Algorithm. So that's going to actually give us the loss, right? And then we're going to take the backward. We're going to propagate this loss backwards, and we're going to optimize our learning rate with atom optimizer. So that's it. That's pretty much training. There's a lot of theory, but we've summarized all that theory in very few sort of lines of code. By the way, this is all based on tch.rs library. It's a very cool library, so I encourage you to go check it out. tch.rs. They have or Laurent has a lot of very cool examples right there. So yeah, you should definitely check it out. And that's it. After we're done, I've commented this code out, but you can uncomment it, and we would be storing our weights, so our learned weights. So that's it. And we'll be running this right now. And how do we predict? So for prediction, it's basically we're going to be, so we kind of set the structure of what the neural network is going to look like, which actually has to have the same structure as we defined earlier. And then on top of that structure, we're going to load the weights, right? We're going to load the weights that we saved earlier, and then we're going to do one forward pass for prediction. So after we do the forward pass, okay, we're ready. Just give me the prediction. What is it, right? So yeah, let's go ahead and run this. So let's go to the terminal. Then we're going to go. So I'm already here in the project. So let's see, just to kind of follow the README. So we've done all this. We are currently in the project, and then, okay, cargo run NLP. So this is the training. And so this iterated, I guess, 30 times, and it still isn't getting to a good level. So let me just do this again. So here, okay, got 83. I've hard coded the 30 epochs in the settings file. So just so you know where it is config defaults 30 iterations somewhere there. Here, epochs, 30 epochs. So okay, back to the to here. So we've trained our model, we've saved our model. Now let's go ahead and predict. And this is our prediction. So basically, as we mentioned, we had a binary classification, and it's saying, okay, I think this is non-mutagenic with this probability. So if we were to discretize this to either 0 or 1, this would go down to 0. So this is non-mutagenic, and this is mutagenic. So in this case, this would go up to 1, and we would say, okay, this is the correct class. And based on our train and test data, we know that 83% of the time it's going to be a correct prediction. Of course, yeah, if you're doing like a serious project, you'd want to make sure to kind of fill in the gaps. And usually we'll try to get this to like 98s or 95s. I don't know. It depends on the use case. And also you need much larger data set. So here, this is 188 examples. So yeah. So we've already kind of walked through the code, through the training code. We've walked through how we store the weights, the iterations. We walked through this. We've walked through prediction already. And yeah, that's pretty much it. So if you want it, so the code that's written here, developed, it's actually based on this paper right here. So it's really heavily based on this paper, which is by like a graph sort of formalization of graph neural networks. So I'd encourage you to also read it. It's really good, and there's a reason that I guess I decided to kind of take this. I don't know, I just thought it was pretty cool, so you should definitely go ahead and check it out. And so maybe just to conclude, as business problems continue to grow in size and complexity, there is a natural requirement, which is kind of like implicit by by ourselves, that solutions need to be efficient and scalable, right? So to me, graph networks is it's shown in the past that it's actually very efficient at modeling relationships, which we can pretty much model anything in graph sort of structures. If you think about it, kind of like in terms of graphs. So the reason that we tried to develop this code in Rust is because Rust is light and secure, and it's actually very fast. So we're trying to, or actually we're in the process of developing a embedded sort of system for deep computational learning. And first of all, the graph frameworks is pretty efficient. Now we're trying to write this in an efficient programming language such as Rust. So with the added properties that it's lightweight and secure. So that's just, whenever we're talking about embedded systems, you're usually going to have these characteristics where you're going to have, think of a cell phone sort of thing. You don't have too much memory. There's no capacity. You're basically constrained on every on every front, right? This needs to be business critical, kind of, and safe, and it process data real time. So it has it's not an easy task, but the Rust language is actually pretty cool. It takes some time to learn, but it kind of accomplishes, or it helps us accomplish these tasks. Second benefit, it's so we're gonna so we can whenever we're talking about distributed computing, usually Docker and most of the container runtimes today are based on runc, and I guess there are some new container runtimes that are up to 6x lighter, and they're written actually in Rust. So we want to kind of build our program inside of these containers, and the reason is that this is going to be integrated into a distributed processing engine. So we want our distributed processing engine to be efficient and pretty much run on any processor you give it. Silicon, semiconductor, transistor-based processor, sort of speak. So this is what we just showed is kind of like a prequel to this distributed processing engine. And yep, that's it. Special thanks to LionTem research team and to HPE. And here are the sources for this article. Yep, thank you.